Let's assume we want to predict the sentiment for a given movie review. So here we have our movie review, and we want to know, does this movie review express a positive or a negative sentiment? So is it positive or negative? So again, to keep it simple here, we have binary classification. So to run logistic regression as a classifier for this type of sentiment analysis, we first have to extract features. And features here are some kind of numeric values derived from the text. So for example, if you look at our first feature x1, we simply count the number of positive words. And positive words we can look up, for example, in a sentiment lexicon. You would see, for example, that enjoyable, let's make this green, would be a positive word, nice might be a positive word, and so on. And we have different kinds of features, like also the number of negative words, how often, if no appears in the text or not, and so on. And it's not here important what exactly the features are. Here we keep it simple and pick these 6 features. And as we stated here, the idea of extracting numerical features from text is a very important part of NLP and will be covered in the subsequent section. So here we basically perform feature extraction. Given our different kind of features, we extracted a value. So here, for example, again, we already saw we have the 3 positive words, nice and great. And we did the same calculations and extraction process for all these 6 features. And now we have basically some kind of representation that we can give the linear regression as a valid input, because all of these are now our x vector. Now that we have our feature vectors, now we can factor in the weights. In this case, we assume that some oracle gave us these weights. So right now we don't care where these weights come from, they are just there. And this is also a good time to include now our bias trick. Again, this is our artificial feature x0, which is always 1, which allows us to introduce simple theta 0 to keep everything consistent and make the math simply easier. So now we have our values and we have some weights that come from somewhere. Right now we don't care from where. So now that we have all these values, we can compute first our linear signal. And the linear signal is just the sum of the weighted features that we saw. So what we do here with these values, we simply say, okay, we multiply all these values. You can consider these theta as the scales or weights or factors of each feature. And then we just sum it up. And if we do this, we get our linear signal as 0.833. And of course, we can do it in a smarter way using the vector product or dot product, which of course gives us exactly the same result, just treating the inputs x and the input theta as 2 vectors. And in the last step, now we can compute the probabilities, which simply means we use this linear signal as an input for the logistic function or sigmoid function, which we do here. So this value we just computed, right? This was our 0.833 linear signal. But in this case, this linear signal is between 0 and 1. This is not guaranteed. So this linear signal can be much lower than 0, can be much higher than 1. So we have to squeeze it into the range of 0 and 1. And for this we use the sigmoid or logistic function. And in this case, if we just plug in a number, we see that the probability that our input movie, so basically x is this movie review, would say that the probability that this movie review is positive is 0.7. And since we have just two outcomes, we can simply say, okay, the probability that our movie review is negative is obviously 1 minus 0.7, so 0.3. And in this case, now we know that the probability that our movie review is positive is calculated as 0.7, which is larger than 0.5. We say that we predict the movie review to be positive and would classify it as such.